Greetings, fellow enthusiasts of the cosmos and seekers of understanding. In the last video, in our quest to understand gravity, we answered the question, how is gravity created? I introduced a new concept which showed the relation between molecular synchronization and asynchronous temporal fields. In consequence, gravity emerges to try to rectify these two opposing forces, which it can inevitably never accomplish. This is why there is always that constant pull of gravity. In today's video, we will discover the origins of time dilation. The phenomenon comes out of Einstein's relativity theory. Unfortunately, Einstein was never able to explain why time differs in different gravitational potentials or for different observers. He merely brought them to our attention. Alas, in this video, I will cover a new concept called space density, which will unfailingly explain many concepts that come out of relativity theory, specifically the equivalence principle and gravitational redshift. In addition, I will answer another all-important question of physics: why does time dilate? So let's get started. There are two main types of time dilation. Time dilation is a concept from Einstein's theory of relativity that describes how time appears to pass differently for two observers who are moving relative to each other, especially at speeds approaching the speed of light. Gravitational time dilation occurs due to differences in gravitational potential between two observers. According to general relativity, clocks closer to a massive object where gravitational potential is stronger will tick more slowly compared to clocks farther away where gravitational potential is weaker. So now that we have an understanding of how time dilation works, the question remains, why does time dilate? So let me answer that for you. This involves a new concept that I would like to introduce called space density. And maybe you're not thrilled about new concepts, but remember, this is science, and exploring new frontiers is what science is all about. And besides, unlike string theory or quantum loop theory, space density actually has some evidence backing it up. And not just any evidence, we're talking about some big players like gravitational redshift and Einstein's equivalence principle, just to name a few, so let's get into it. Space density is exactly like it sounds. Imagine you have a jar full of space or space-time. Cram more space-time into that jar. What you've done is increase the space density. The only way to do this in reality is to take your jar with you deeper into the Earth, and the space density in your jar will keep increasing the deeper you go into Earth's gravitational field. The basic principle to remember is that space density increases in a strong gravitational field and decreases in a weaker one. But still, what is it? Okay, so look at it this way. If I have a distance of 1 light year, it will take 1 year for light to travel that distance. But if I double the space density, it would take that light 2 light years to travel that same distance. So you ask, how can you just stuff more space into space? Because that seems like a bizarre thing to do. To answer that question, let us take a look at some experiments and models that can help us explain space density better. I already mentioned them earlier. The first one is gravitational redshift. In April 1960, at Jefferson Laboratories, Harvard University, gravitational redshift, which had been predicted by Einstein, was confirmed with the Pound-Ripta experiment. Gravitational redshift predicts that photons emitted from a source in a stronger gravitational field will lose energy, shift to longer wavelengths, as they move away from the gravitational source. In this experiment, gamma rays fired up an elevator shaft were shown to have a slight red shift, as predicted by general relativity. The common explanation for this is usually that gravity pulls on the wavelength, causing it to lengthen, thus losing energy. But of course, that just makes for a good analogy. It is not what actually happens in reality. The space density version explains gravitational redshift more mechanistically. Think of it this way: if space expands, then anything within that space will expand as well, at the quantum scale anyways. So to explain gravitational redshift with space density, you could say that when light travels from an area of high space density, strong gravity, to an area of low space density, weak gravity, then space becomes less dense, and as a result, a photon's wavelength also lengthens. This is due to the corpuscle nature of photons. Now let's take a look at how space density relates to Einstein's equivalence principle. This principle, if you are familiar with it, asserts that in an enclosed system, one cannot tell the difference between being in an accelerated body or being under the influence of gravity. So it is the equivalence between acceleration and gravity that we are talking about. So you wonder, well, great, how does space density explain this one? And the answer is actually quite simple. Imagine you're standing on the Earth with a space density of x. In another scenario, you're in a rocket ship floating through space with a space density of y. At this point, x is greater than y. As your rocket ship accelerates, you would in fact be going through more space within a specific time interval than compared to when you were just floating around, so y would start approaching x. This is because traveling through more space actually increases your space density in much the same way as running increases your air resistance. So the reason why there is an equivalence between acceleration and gravity is because at a certain point they have the same space density, at some point y equals x. Yes, that's right. You heard me correctly. Space density doesn't just depend on the strength of your gravitational field, it also depends on your acceleration. Thus, in relation to the equivalence principle, acceleration and gravity can be equivalent due to their space density being equivalent. Okay, so there are some analogies, and I know it isn't perfect at this point because it's still fresh in your mind. But as we progress through this series, you will find that space density keeps answering a lot of questions that previously were left unanswered. So, let's move on for now, because I will always be explaining more in the next video and coming back to previous ideas. For now, let's explain that question which I mentioned at the beginning. Why does time dilate? So the reason time dilates is because of space-time density, which is similar to space density, but now we will account for the time portion of it. We know space and time are intertwined, so what happens to time when space density increases or decreases is the exact opposite. Here's a general rule to help you remember. As space expands, time contracts, and as space contracts, time expands. Pretty simple, it's vice versa. So think of it this way. You're traveling at half the speed of light, and based on the theory of relativity, your time would slow down considerably compared to the person standing on Earth. So if 1 year goes by for the bystander, you may experience a time of like 40 years. This is partly what happened to Matthew McConaughey in Interstellar when he met up with his much older daughter, but most of the time dilation was probably due to the black hole. Does not matter. But let's run through it so you're accelerating through space at half the speed of light. Based on our previous assertion, your space density has increased, which means it has contracted. That also means your time has expanded. Since time has expanded, this means you have more time than the person waiting for you on Earth. So the reason time dilates is because whether accelerating at high speeds or moving through gravitational fields, the simple explanation is that space-time density can oscillate, and thus so can time. I know you will have to ponder that one for a bit, and most likely watch this video a few times before you can wrap your head around it. I hope you do. So in conclusion, the concept of space density offers a new perspective on time dilation. By understanding how space and time interact within different gravitational fields and velocities, we can better comprehend the mechanics behind time dilation. As we continue to explore these concepts, space density may provide answers to many previously unanswered questions in physics. In the next video, we will delve deeper into these ideas and explore further implications of space-time density on our understanding of the universe. This concludes our exploration of why time dilates. Please subscribe and smash that like button to keep receiving groundbreaking content. Stay tuned for the next video, where we will continue to unravel the mysteries of the universe. Most importantly, we will cover anti-gravity concepts and models, and how one might begin to conduct experiments in this ever-elusive realm. Bye for now.